So let's do a brief review. So last time, where do we leave off? So we talked about the RMS norm, SWI/GLUE implementation, and yeah, we discussed the idea behind multi-ed group query and multi-query, and didn't quite do the to-dos here, right? Okay, let's do a brief review. Okay. So the idea is we're gonna crack open OpenAI's GPT OSS model, which is open sourced, and look at some of the key differences in the architecture that's different from what we covered so far during the lectures. So notably, MOE part was a lot larger, had a lot more parameters. And if you compare the 20 billion model with 120 billion model, almost all components were the same, except the number of layers and number of experts in MOE. And last time we discussed, okay, so what's different in their SWI/GLUE implementation in the final MLP step. So we still have the RMS norm. So let me just connect while we are at it. And just to give you a heads up, we have lecture series about OSS. And then we have another final exercise notebook where we introduce you how to use Hugging Face so that you can download pre-trained models and fine-tune and everything. And then you'll be ready to do your project. And after then, we're going to start the normal lecture series. All right. I wish I could include another lecture on how to use Claude Code, but we have to have some balance between theoretical, algorithmic aspect and exercise. So we won't have time to cover Claude Code. But these days, I use it almost every day to code, and if you haven't tried it yet, please try it as soon as possible. You're falling behind if you don't use Claude Code these days. So the idea is you keep prompting, and AI tool will automatically change the code and execute the result, and it can do multiple rounds of code edits and execution without you in the loop. So your productivity will be a couple orders of magnitude different if you use Claude Code to code. All right, so we already talked about this. So what's different in OSS's implementation of SWI-glue? So the basic equation looks pretty much the same. So you have x gate, x linear. You take SNU of x gate, where SNU is x times sigmoid of x, element-wise multiply with x linear. But the key difference is you take your input x, multiply with fused weight matrix, and for every even dimensions, it becomes the gate. Every odd dimensions, it becomes the linear. So gate and linear is interweaved. And also additionally here you need to do clipping on the gate. So here, gate specifically, you only want to clip the upper bound, so it doesn't exceed this limit above. For linear, you want to clip it for both the lower and upper bound, so it's between negative limit and positive limit. And then you add 1 here, and these are the key differences. So we implemented this together last time, and you take as input the matrix multiply Z here, and every even dimension, odd dimension becomes X gate and linear. And you apply the clipping on the gate and linear, and you compute SNU here on the gate, and you do element-wise multiply between the SNU output and X linear plus 1. That was the implementation that we done last time together. And RMS norm, yeah, pretty much we covered this last time. Yeah, so here I just wanted to mention we're going to swap in layer norm with RMS norm, meaning we're no longer going to do mean subtraction. So the output of RMS norm is no longer going to be zero-centered. Okay. All right. So that was pretty much last week, and we talked about the idea behind multi-attention, multi-query attention, group query attention, where the idea is we still have the multiple query heads, but the idea is we're going to share different key heads and value heads, so we can reduce number of activations for efficiency. So to take this to extreme, in multi-query attention, you have multiple same number of query heads, but you have a single key head and value head. So every single query shares the same key and value. And in the middle, you have grouped query, where a set of queries, subset of queries, share a single key and values, and so on. And another subset of queries share the same key and values, and etc. So in GPT-OSS, they use grouped query attention with 64 query heads and 8 KB heads. So there's 8-to-1 ratio, where 8 queries share a single key and value. And also to compute each query key and value activations, they do fused projection, meaning they take X and multiply with the big concatenated QKV matrices. So you don't do 3 separate matrix multiply. You do a single matrix multiply with the larger matrix. So this may or may not be faster than separate matrix multiplies, and it depends heavily on GPU spec and the memory bandwidth in the underlying GPU. And to mention the practical side, and it may be the case that some of the layers, so let's say we fix a GPU type, it's fixed, it's constant, And in some of the layers, it might be faster to do fused, and in some other layers, it might be faster to do separate projections. So there is combinatorially many different possibilities that's going to be optimal. But here, they just apply fused projection for all layers. But this is not, to be precise, this is not optimal. All right, so you guys can read about the KB cache size. So in multi-head, if you have H query heads and H KB heads, what is the KB cache size per layer? So you have H heads, and in each head you have head dimension times sequence length, number of key activations, and times 2 because one for the key and one for the value. Okay, so we have per each head key, oops. Okay, per each head, H, we have two things, one for the key, one for the value. And in each head, we have dimension times sequence length. Sequence length is number of tokens. And the extreme guy, multi-head, we have H query heads and a single KB head. So number of the KB cache size is 2 times DH times N. KB cache size meaning the yellow and pink boxes here. Group query attention, you multiply this guy by this ratio between query and KB heads. Here, in this example, G is equal to 8. All right, so so the easiest way to implement this is what? You just copy these blocks according to how many copies you need based on number of inputs. So here you have 2-to-1 ratio. So you just simply copy this twice and carry out the attention as usual. So that's what we're going to do here. So we're going to have this helper function where you take a tensor X of shape, batch size, number of KB heads, sequence length, and head dimension. And n rep is number of repetitions, number of times to repeat each KB head. So if the repetition is 1, then you don't need to do anything. Else, you need to do something here and reshape the output. So in the interest of time, let's just do this together. This is a single line, then you need to edit. You take your input X, and you can use this expand method. So you can repeat each KB head n repetition times. Finished copying? Yes? So this is the newly inserted dimension with non-key here and repetitions. And we're going to reshape it so these two get merged into a single dimension. Right? Need more time? How many of you finished copying? All right, let's move on. Okay, so let's just briefly check the shape. So input shape was batch size, number of KB heads, sequence length of 10, head dimension of 4, and to print out the input, input 0 and input 1 looked like this. And after we execute this repeat KB method with n repetition equal to 4, then this guy must have been repeated 4 times. So if you query the first and the fourth entry after repetition, it's still the same. This guy got repeated 4 times. And same thing for below. This guy must have been repeated 4 times, this entry here. So if you query the 5th one and the 8th one, still the same. Okay, so this time we're going to implement the grouped query attention together and check the shape and what else? And check the memory of the KB cache size. Okay, so all right. So I already explained the basic idea in grouped query attention. You want to save on the KB cache size by sharing the KB caches for multiple queries. And as I mentioned, we're going to use a fused KB cache projection. And we're going to use RMS norm. And we're going to do pre-normalization before attention. And we are going to eventually need to do some slicing so we can have variables for query key and value after we do a fused projection. Okay, so if you have this input X, batch size, sequence length, some dimension, and this is the fused matrix. It's a large concatenated matrix of size dimension by head dimension. And here, let's look at the dimension. So n heads is number of query heads, and we have times 2 plus times 2 of number of KB heads. So the fused projection is you take your input X, multiply with this large matrix, and you're going to get some output, and we need to slice this according to the respective dimensions. And the Q dimension is number of heads times head dimension. So we don't reduce on the query heads. We only do reduction on key and value heads. So each KB dimension is going to be number of KB heads times head dimension. So this is going to be a lot less than this guy here in grouped query attention. So for slicing the result, we already know the dimensions for Q, K, and V here. It's already given to you. So given the output here, the first Q dimensions are going to be the query activations. And from the first Q dimension to whatever is plus KB dimension, this is going to be the key. And basically, if we move same amount, then that's going to be value. So we take out the first Q dimensions, that's going to be Q here, and rest of them is going to be same dimensions. So they take up equal space. So we split the rest of them by half. That's first half is key, second half is value. Okay, so after that, we're going to reshape the output. So it's batch size, number of heads for the query, sequence length, and head dimension. And for each key and value, batch size, number of KB heads, which is less than number of heads, times sequence length times head dimension. Okay, so this is what we're going to implement. So here, we now have additional parameter here, number of KB heads. If this is equal to number of heads, then that's equal to standard multi-head attention. If this is less than a number of heads, then it's implying grouped query attention. So, and of course, these has to be divisible, so we can make n-to-1 correspondence. So let's see. So if you divide number of heads by number of KB heads, that's the number of repetitions you need to do to plug in to our helper function here, repeat KB, right? And here's your first to do. You need to define fused KB projection and output projection. And in the for step, you need to follow these steps. So first, apply fused KB, QKB projection, split the output. So take out the first head dimensions, call it Q, rest of them is KB dim. So these are already given to you above here. And once you know the dimensions, rest of them is easy. You just need to do indexing. And we're going to give it a name, Q, key, and value. And then we're going to reshape it so it's of size, batch size, number of heads, sequence length, head dimension. Or this may change based on input. So batch size, number of KB heads, sequence length. Okay, and finally, we're going to repeat the KB head n repetition times so that we can use the repeat KB head method. This is just to help you understand what's inside, but in real practice, we're not going to repeat KB cache. That defeats the purpose. It's going to be broadcasted automatically. So rest of them is the same. You add in the mask and apply softmax, matrix multiply, and matrix multiply with output matrix. And here we're going to check the size, make sure everything looks correct. And let's take some moment to implement to-dos here in the group query attention. Okay, it wasn't very difficult, right? Okay, so what are the to-dos here? QKB dimension out. All right, so in the constructor, we had to define dimensions. QKB dimension, head dimension times number of heads, plus 2 times number of KB heads. So this is the dimension corresponding to all the queries and all the Ks and Vs. Right, number of heads for the query heads. For each key and value, number of KB heads, right? And so we define 2 matrices. First matrix is the concatenated large matrix W, which is of size dimension times QKB dimension. And the out matrix is number of heads times head dimension times dimension. Where the head dimension is given already in the constructor. Okay, so once we have that, in the forward method, given the input, we just matrix multiply with this large matrix W, and that's the output. So this is the fused projection part. Fused QKB projection is this line here. Second line, what are the dimensions? The Q dimension is number of heads. This equals to number of query heads times the head dimension, and each K and V is going to have number of KB head dimension times number of head dimension. Can I move on? Okay. All right, so after we do fused projection and get the dimensions set, then we just need to do slicing. So first, query dimension is key. Rest of them, half and half, is going to be key and value. And then we're going to reshape it so it's of size, batch size. Batch size, number of KB head, sequence length, and head dimension. So we're going to reshape it and then transpose the second and third dimensions so it matches the expected shape here. Okay, and how many repetitions do we need to do for key and values? We need to do it for number of repetitions, which is in the constructor defined as number of query heads divided by number of key value heads. And once we have that, then we're going to execute the method we just implemented together. We're going to take the key and value and repeat it this many times and do matrix multiply, and rest of them is exactly the same as before. Right? All right, so let's move on. I don't know if I executed this cell here. And let's check the dimensions. All right, so in multi-head attention, this exactly same class, but number of KB heads is set equal to number of heads. So this is the standard multi-head attention. So here we're going to check the shape, and we're going to repeat this where we reduce on the number of KB heads. So this 2 means 4 query head is going to share a single KB head. So the ratio is 4 to 1. And if I set this equal to 1, all 8 query head is going to share the same single key and value head. Okay, so let's check the shape. So for the fused KB, it maps to 192 dimensions, 64 all 64 query heads, key heads, and value heads, and output is same as the input dimension. And here in, for example, multi-head, multi-query attention, we have 64 projecting to 80. So I'm slightly confused. Okay, let's do this first. So here there is 2 KB heads. So 4 query head is going to share a single KB head. So 4:1 ratio, or divided by 4. So what is it project? And there is 60. Right, so this seems correct. So 4 query head is going to share a single K and V. So there's 16. So divide this number by 4. There's 16 key head and 16 value head. So add this up, and the fused projection is projecting from 64 to 96. Seems correct. And if I set this to 1, then I'm confused. Sounds like this has to be equal to 1. Number of, it's, yeah, right. So here, this is the actual full dimension, not the number of heads. So we need to multiply this number by the head dimension. Okay. Which is head dimension, we set it to dimension divided by number of heads. Dimension is 64, so 64 by 8. Yes. This is the head dimension for a single key head dimension for a single value head. All right, so next cell is going to showcase how much KB cache size can be decreased with these techniques. So x-axis here is the contact length, or the sequence length in log scale. Y-axis is the total KB cache size in gigabytes. So multi-head attention is the blue here, which is the classic setting that we discussed so far. And in grouped query attention, as we compress number of required KB heads, then you can see the savings in terms of the memory is quite significant. So this is using the code that we just implemented together. So we're going to compare multi-head attention, where it has 32 key activations and value activations. And we're going to compare it all the way to multi-query attention, where there's a single KB head that's shared for all queries. So in terms of megabytes in the KB cache size for our small input, so our small input, let's see. It's going to be sequence of size 4,096 number of tokens, and 32 layers, and the dimension 4,000 as well. So for this small sequence, so we only have 4K tokens here. The savings in terms of the KB cache savings is quite significant. Okay, so compare multi-query attention, for example. It reduces the KB cache size by 32-fold, and compared to the multi-head attention. If you use GQA 8, reduces the KB cache size by 4 times. So savings is quite significant. Because last time, as I told you, as we increase the token length, as we do longer and longer context generation, then the bottleneck here becomes the size of the KB cache in the memory. Okay, next up is LoRA. Stands for low rank adaptation. We haven't talked about this so far. So this is a new concept. So the fundamental difference here is, so far we assumed the model weights are trained for you, and you're going to use it to generate something. But what if you want to fine-tune or retrain the model on a specific data set, for example, or some specific task? Then you need to do what's called fine-tuning. So all this means is you initialize the weights with the given trained weights, and you start training again on a different loss objective or a different data set, whatever you want. So as opposed to randomly initializing your weights, you're going to initialize the weights to a pre-trained model weights. And there are some implementation details you need to worry about, like learning rate, because compared to training from scratch, meaning training from randomly initialized weights, you need to decrease the learning rate quite significantly compared to a randomly initialized model, because you don't want to change the model weights very much. You don't want to deviate too much from the foundation model's weights. Anyways, so for example, GPT-OSS 120 billion has 120 billion parameters, which is very, very large, and it needs many GPU computers to train models with this many weights. So practically what you can do is, smaller model, 20 billion model, if you store the optimizer states alone, it would require 700 gigabytes. Optimizer state means all the model weights and activations. Do you know, for example, if you have a GPU, do you know how much memory it has? A single GPU, a modern GPU? Just to give you some context. 80 gigabytes? For expensive GPU, yes. For moderate ones, like Ada 6000 GPU has, I think, 24 gigabytes or something like this. So this does not fit in a single GPU. So you need multi-GPUs, lots of them, to train these models. And you need to worry about communicating between GPUs and all these things, and different machines as well. So what can you do realistically? What we can do is low-rank adaptation. So LoRA, the idea is this is the original weight W. We're not gonna backprop here. We're gonna just fix it as is. We're gonna add in some low-rank matrix that we're gonna backprop through. So let's say loss function is here. We're gonna put a stop gradient to W, so W doesn't receive the backprop gradient. It only receives the gradient through this low-rank matrix. So why is it low-rank? Matrix A is upsize D in times R. R stands for the rank. B is upsize R times D out. So W, the size of W is D in by D out, which is very, very large. But this R number is very, very small. It's much smaller compared to the smaller of the two. This is a very small number. So if we backprop through A, backprop through B, then the actual number of parameters that we're going to change is very small. It's maintainable. It fits in a single GPU. Because, why? Because individually these matrices are very, very small. Okay, so pictorially, input comes in. For the 4 pass, we're going to matrix multiply with W prime, which is adding the pre-trained weight W, plus some constant times low-rank matrix AB. We do 4 pass with W prime. Backward pass, we only backprop through matrix A and B. And this number R is very, very small. All right? And matrix B is initialized to all 0. Meaning, if you initialize the weights to pre-trained weight, initially, if you do a 4 pass, this matrix is all 0. Initially, during the 4 pass, it sees no difference between pre-trained weights and whatever is initialized through LoRA. Okay. Initially, we simply match the setting that we was trained on, and then we slowly backprop through matrix A and B to make minor adjustments. All right. So the idea is very simple, right? Okay, so how many do we have? All right, so I think this is the final to-do for this notebook. We're going to implement the LoRa linear. So it's going to wrap the existing linear module with what we are implementing here. Has 3 parameters. Linear, this is the original frozen linear layer. The pre-trained weights. Rank integer is going to designate how much rank we're going to use, or basically the size of skinny portion of A and height portion of B, and alpha is some scaling factor. All right, so first we need to initialize the matrix, low-rank matrix A and B. And remember, B is initialized to all 0s. And we need to really make sure the gradient does not flow through the original weights linear. We're going to do that by, in PyTorch, this has required grad flag where you can set to false. You can tell PyTorch to do not backpropagate through this matrix. Same thing for the bias. And like I said, during the for pass, we're going to do a for pass with W prime here, which is original weight plus some scalar times matrix A and B. So we're going to do a for pass computation with W prime. That's what you need to implement here. So once you implement this part, run this cell, and we're going to check some parameters and try to compute the ratio between the LoRA parameters, basically number of parameters in A and B, versus a whole thing. So two parts: initialize these weights and implement the for pass. While we're implementing, just to make a clarification here, when I say optimizer states, if you still remember the optimizer lecture, we not only need weights and activations, we need to store in the memory the momentum, velocity, and what is the size of the momentum and velocity? Basically, the formula looked something like this. You do matrix, you element-wise multiply momentum or velocity with the gradient. So it has to have the same size as the gradient, and gradient has the same size as the weights. So it's not just the weights and activations you need to store in the memory. You also need to store equal amount of parameters for the momentum and velocity, and that's easily 3x or 4x of the weights. So even though the parameter is quite small, in order to maintain everything in the memory, that becomes quite huge. Okay, let's look at it together. So we need to initialize matrix A and B. Matrix A, we're going to initialize it according to however we were initializing the weights before. So we create some random matrix divided by a number of square root of the input features. input dimension, and B is initialized to all zeros to make sure, at least in the initial stage, during the 4 pass, it's same as computing the 4 pass with the original weights. That's for initialization. For the 4 pass, okay, so it was asking just the LoRa part, and it's going to add in the original with LoRa, and LoRa is some scaling times x times a times b, and this is the lowering part. You add it to the original weights, and that's how you do 4 pass. So it was quite easy. Okay, so some more time. Do you need time? Okay. Can I move on? All right. Okay, so for D in, D out of 64 times 128, for a rank of 4, meaning we have very skinny and short and fat matrix A and B, so we're only going to use rank of 4. So in this setting, it's first checking if there's any difference between the 4 pass using the original weight versus LoRa. The difference is 0, like expected, because B is initialized to 0. And original parameter for this single matrix multiply was 8,030/320, and if we use rank of 4, LoRa parameter is about 600. So the ratio of weights you need to train if you use LoRa versus full matrix is about 9%. So this is how you bring down the number of parameters to fine-tune efficiently. Okay, so let's do a little more analysis. So we have prepared this cell for different layer sizes, 1,000 by 1,000, 2,000 by 2,000, 4,000 by 4,000, 4,000 by 11,000, for varying ranks. So on the left, you have the trainable parameters if you use LoRa versus full. Y-axis is log scale, and x-axis is a rank in LoRa. So for example, if you compare this full matrix of 1,000 by 1,000 dimensions, as you increase the rank here, this dotted line is with the full matrix. You have significant savings in the training parameters. And same thing for this large matrix, the red matrix here. As you decrease the rank in LoRa, the gap between the full versus LoRa parameters is quite significant. In terms of the ratio, here y-axis is how much fraction of the full parameters we're going to train with LoRa, and x-axis is the rank again. And for example, for this large matrix, as we decrease number of rank here, for example, if we do, I don't know, 35 ranks, we're only going to use 1% of the parameters. And for this small matrix, if we use, I don't know, rank 5, we're only going to use 1% of the parameters. So we have savings about a factor of 100. So for example, for 4000 by 4000 fully connected layer, which has 16 million parameters. If we use Senko 4, you only use 0.2% of the parameters. If you use rank 16, you only use 0.78%. So it brings down the complexity during training quite large. So if you ever need to do fine-tuning on a custom dataset or a custom loss objective, then this is the way to go. You download pre-trained large model from Hugging Face. We're going to cover Hugging Face next lecture or next lecture, and then use LoRA to fine-tune. And you may or may not need to fine-tune your model for the project. It's open-ended. It's up to you. And we talked about two important things: LoRA for fine-tuning, and group query attention to save number KB cache size. So we have procured a good GPU for the project. For each team, you're going to have L40 GPUs. Let's see, has 48 gigabyte of memory and lots of CUDA cores and bandwidth of 800 gigabytes per second. And you're going to have access to a single L40 GPUs per team. And I think the deadline to form the team is it today? Right, so there's a sign-up sheet on sign-up spreadsheet, right? Yes? Okay, so you can decide to form your own team, or if you don't, you can partner up with other students. We just needed to wait a bit, so it's past the drop deadline, so we don't have the trouble where some teams have like a single person because 3 person dropped the class or whatever. All right, so I think it's gonna be a fun project, and I think we covered quite significant amount of the modern LLMs. Next up, I think it's going to be lecture 12, and covers additional tricks that's present in OSS model. And MOE, we talked about this, but the specific detail, implementation detail is slightly different for OSS model. And it also has this thing called sliding attention, window attention. So do you really need to do full attention for every single layer? The answer in OSS model is no. For some of the layers, they use window attention, where you only attend to immediately near tokens. And some of the layers, you do full attention. So it gives you some saving on the memory as well. And what else? Yeah, and that's pretty much the techniques that we wanted to cover. And next up, beyond this, is the final hands-on lecture using Hugging Face and some PyTorch syntax. All right, thanks. That's it for today.